All right, so now we have all the boring stuff over and done with, all the significant digits in scientific notation. And yes, you do need to keep that in mind for the rest of the unit because we're going to be using it, but that's the boring stuff. Let's actually get on to what the heck physics is. It's all this stuff. It's basically anything you can think of in science, but then looking at how it works, the mechanisms behind it, which is awesome. So we can look at things like sound and friction, gravity, force. That's all stuff that we look at in physics 20, really in depth. And then in physics 30, we go into things like electricity. How does that work? How does light work? How does magnetism work? What is the physics behind atoms? What's keeping them together? What is going on there? So we get to go over all that stuff. Physics is super duper awesome. I hope you take it 2030. But just keep in mind, you do need to be able to do all the math behind this as well. And that is a big part of physics as well, as mathematically proving these different things in our universe. So physics, this is the knowledge of nature. It's the natural science, involves the study of matter, its motion, its behavior, and mathematically backing that up. But of course, it needs to be through space and time, because when we don't include space and time, well, actually, that's another branch of physics, when there's no space and time, but then things get really crazy and really weird. So we're just going to keep it to space and time here because we can't get there right now. You need, like, the math skills are insane that you need for that. It's just crazy. So we're going to do mostly energy and force in physics, in science 10 for physics. So let's get started, you guys. I'm so excited. We're going to start with the most basic principle in physics, and that is motion. Okay? And I know it's like, whatever, yes, things move, like, what's the big deal? How do we describe or define motion? And I know it's a silly thing. It's like, okay, well, something was in one place and now it's in another place, and therefore it had to have had motion. But really, these beginning and ending points that we choose are arbitrary. So we have this imaginary line joining an object to a reference point, and of course it's changed in length, direction, or both. And when you really think about it, motion actually isn't quite as easy as you always thought. Because have you ever been in a car that's moving, and then the car beside you is moving at the exact same speed? It doesn't look like you guys are moving. It looks like your background's moving, but like if you look at the other car, it looks like you're just like staying still together. Or how about you're sitting in a car and you are sitting still, and then the car beside you starts to back up, and you think that you're backing up because the car beside you is. So motion actually isn't as simple as you really think. Once you really get into it, there are a lot of different things that we can consider when we're talking about motion. But we're going to start with the basics, like the basic. And that is when you have motion in a straight line at a constant speed. And that is called uniform motion. So when a car here is going in a straight line, it's moving 4 meters every 2 seconds, right? So after 2 seconds, at 4 meters away from its starting point right here, which of course is a random arbitrary starting point that we're choosing. And then of course after 2 more seconds, it's at 12 meters away. So that's a total of 6 seconds afterwards. That is uniform motion, when something is covering the exact same distance over the same interval of time. Okay, that's what uniform motion is called. Non-uniform motion is what we experience most of the time. That's when you have change in speed, change in direction, both, right? A roller coaster is constantly changing its speed. It's constantly changing its direction. And so that is non-uniform motion. And that is a lot more difficult to really figure out what's going on, because then of course we don't have these nice changes over time. So we're going to look at uniform motion a little bit more at this point than non-uniform motion. So let's talk about calculating speed for uniform motion, because that is very, very important. So we're going to start with the most basic equation that you can start with in physics, and that is the equation for average speed. Okay, so this is the equation for uniform motion. You're covering the same amount of distance over the same amount of time all the time. And so, of course, average speed is just distance traveled over time elapsed. Okay. We always want speed in meters per second. I guess not always, but often. Okay, so your distance here has to be in meters and your time is in seconds. And then, of course, your speed, therefore, is in meters per second. So, of course, here we have V right here, and this is speed. Y is V speed. Y is an S speed. Okay, I think we'll figure that out in a minute, but let's just focus on this for a minute. D is your distance moved, okay? And T, of course, is time. Now you're like, what are these funny little symbols right here? You might know because of math, but if you don't, that's a delta. That just means change in, okay? So what's your change in distance over your change in time or your time interval? And that's all you want to know. So change in is equal to final minus initial, except for time. I always hate that they put that in front of time. Like, we can just put T there for time elapsed. So that's on your data sheet, on your formula sheet that you were given at the beginning of the year. And it has a delta T there just to say change in time, but that does not mean final minus initial for time. That just means, if like 30 seconds has elapsed, then 30 seconds has elapsed. Just use that. Don't worry about change in time. But if I want to know change in distance, well, that's just the final distance minus the initial. So if someone who is not practicing good social distancing was only a meter away from me, and so I asked them to move further away, so we had good social distancing practices, and so they moved so they were 2.5 meters away from me, then what was their distance? Well, it was that 2.5 minus the 1, because they were already a meter away, so they moved 1.5 meters. Right? So that's what that means, the final minus initial. Okay, so that's your equation for average speed. I'm going to get rid of all this mess that I wrote on it, so you can see it just as beautiful as it is. But this is such an important equation. It also gets a lot more important in physics 20 when you have to know when to use it and when not to. But of course, I'm not going to get into that. I want to, but I won't. So that's your bread and butter of physics in the Science 10 unit. Average speed, V equals D over T. We're just going to be using that equation a gazillion times. So let's start on a few examples. All right, so we have this owl able to drop 1.3 meters in 0.8 seconds to capture its prey. So we want to determine the owl's average speed during its descent in meters per second and kilometers per hour. So we always start with V equals D over T. Now, of course, we have to ask, what is the distance? Well, it says it's able to drop 1.3 meters. Meters, that's our distance right there. So there we go. That's the D. Okay, so that's 1.30 meters. Then we divide that by, we have our T right here, our time. That's 0.80 seconds. So that is the time. And so, of course, 0.80 seconds. So we'll just plug that into our calculator as 1.3 divided by 0.8. That's all you got to do. And you get 1.625. What are your units? By the way, in physics, you always have to have units. You can't not have units. If you don't have units, have a mark off. Okay? You have to have units here. That is meters per second. Okay. Are we done? So we aren't actually. We have to do something because we need to look at significant digits. Okay? So this is the thing where significant digits, again, it's never going to be said that you have to put into the correct number of significant digits. It's always just assumed, okay? So we got to look at this and figure out how many significant digits do we need. So the two things we're given, so keep in mind we are dividing here, so we need to use the rules for dividing. We have 1.30. How many significant digits is that? That is 3 significant digits. Okay, and then we have 0.80 seconds. How many significant digits is that? Remember, leading zeros are not significant, so that is not a significant digit. So this only has 2 significant digits. So that's gonna try and trick you because only the 8 and the 0 here are significant digits. This leading 0 is not, because leading zeros are never significant digits. This 0 after the 8 is, though, because remember, any 0 that comes after non-zero digits is significant. So what does our answer need to be in? It needs to have 2 significant digits. Okay, so if we go back to our answer here, we have the 1 is a significant digit, and then we're at the 6, we're gonna have to round. So our answer is really 1 point, and then do we need to round the 6 up? No, we don't, because afterwards there is a 2, so that means we do not round it up. So we just leave it as 1.6 meters per second. And there we go. That is our final answer. So just keep in mind, if you do not put the correct number of significant digits or units, that could be losing you marks, even though you have the correct answer. Okay, let's do a few more. Okay, so the same thing, this owl is capturing its prey, moving 1.3 meters in 0.8 seconds. So we just did this, but now we want to determine the owl's average speed and its descent in meters per second and in kilometers per hour. So we already did meters per second. We figured out meters per second. Now we need to do kilometers per hour. So remember, this is when we need to use that factor label method that I taught you about earlier. Now, one note, so we know that it was 1.6 meters per second, right? One note, when you are going back to conversions, I would rather that you use the more accurate answer rather than the rounded answer. And then, of course, we are going to round at the end because we still need 2 significant digits, okay? But instead of just using 1.6, I'm going to use 1.625 again because that's the more accurate answer, is it not? It absolutely is. Okay, so remember, we want to change meters per second to kilometers per hour. So I'm going to use this factor label method where I make other fractions here. Okay, and of course, I want to set it up so the units I don't want anymore cancel, and the units I want are left in the places that we want. So here we have meters on the top, so I need meters on the bottom here, and we want kilometers on the top of the fraction here, so I'm going to put kilometers on the top. And then I know the relationship between kilometers and meters. I know for every 1 kilometer, I have 1,000 meters. So I just fill in those numbers as I know them. And then we want to get rid of seconds. That's on the bottom of the fraction. So here it needs to be on the top. And then I want hours on the bottom of the fraction. And then, of course, what relationship do I know for hours and seconds? I know that for every 1 hour, I have 3,600 seconds. Okay, so what am I going to do here? I'm going to take 1.25. I'm going to divide it, 1.625, sorry. I'm going to divide it by 1,000. And then I'm going to multiply that by 3,600. And that's how we can get kilometers per hour. Because remember, it's always about canceling out the units. Meters on the top here, meters on the bottom, those cancel. Seconds on the bottom here, seconds on the top here, those cancel. What am I left with? Kilometers on the top, hours on the bottom. Look at that. It's kilometers per hour. So if we calculate this on our calculators, 1.625 divided by 1,000 times 3,600, we get 5.85. And of course, what are our units? Kilometers per hour. One problem, how many significant digits do we need? We need 2 significant digits because this guy is only 2 significant digits. So don't let that trick you. So what am I going to do? Well, of course, 5 is going to be the first one and 8 is going to be the second one. But what comes after the 8? It's a 5. So I actually need to round that that 8 up to a 9. So my answer should be 5.9 kilometers per hour. There we go. We are done. So sometimes you are given something in meters per second and we'll need to convert it to kilometers per hour or vice versa. So please remember that skill. Let's do one more. So David is driving his quad 25 kilometers into the back country to get his favorite lake to fish for trout. That sounds like a really great social distancing activity right now. So it's taking him 2.5 hours to get to the lake. We're going to determine David's average speed in kilometers per hour and meters per second. So looking at our units here, it's going to give us kilometers per hour right away. Okay, so of course we know V is equal to D over T, distance divided by time. Okay, so we want average speed. So his distance was 25.0 kilometers divided by 2.5 hours. You can put that into your calculator if you don't know it, but hopefully you do, because that should just be 10, right? And that is going to be kilometers per hour. Okay, double check how many significant digits do we need. This guy right here has 2. This guy right here has 3. So of course we need 2 significant digits. Look at that, 10 has 2 significant digits. So there is our answer in kilometers per hour. Perfect. Okay, so now we need meters per second. So I'm going to take this 10 kilometers per hour and turn it into meters per second. So how are we going to do that? Again, our factor label method. We have 10 kilometers per hour. Multiply that. We're going to have 2 fractions. Okay. So first, let's deal with the kilometers. We don't want them anymore, so they got to go on the bottom of the fraction because this guy's on the top. And of course, we want meters on the top of the fraction. What's the relationship there? For every 1 kilometer, I have 1,000 meters. And then hours, we want to get rid of hours. They're on the bottom right there, so I'm going to put them on the top. And then of course we do want seconds on the bottom. And what do we know? For every 1 hour, we have 3,600 seconds. All right, so what does that mean? What are we going to do? We're going to take 10 and we're going to multiply it by 1,000. And then we're going to divide it by 3,600. And then we should be able to get our answer. Okay? And that is 2.7 continuing, so I'm just going to round that up to 2.8, which is the correct number of significant digits, because remember, we need 2 significant digits. If we needed 3, it would be 2.78, of course, but we only need 2, and there we go. We have our correct number of significant digits. Yay! Not bad, right? It's just dividing numbers. Let's do one more problem. So here we have tuna that can swim with an average speed of 30 kilometers per hour. Hold the phone. What did you just get? You got the speed. We do not have distance or time there. That is speed. Have we ever had a question where we've had speed first? Not yet. Let's keep reading. Tuna maintains its average speed. How many days does it take to cross the 5,000 kilometer width of the Atlantic Ocean? Okay, so a good first step when you're like, okay, I don't exactly know what I'm doing, just write out what you have. Here you have speed, V is equal to 30 kilometers per hour. And 5,000 kilometers, oh, that's a measure of distance, equals 5,000 kilometers. And what do we want? What are we trying to find? It says, how many days? That sounds a lot like time to me, does it not? So we're looking for time. We're looking for it in days. We're not going to get it in days to begin with, but that's okay. So let's do it step by step. First of all, what is our equation? We know it. It's V equals D over T. Okay, we don't want speed anymore. We need to solve for what? T. Okay? So I actually did this on a previous video, so hopefully you do remember. But first off, t is in the denominator. I cannot solve for something that's in the denominator. That does not work. So we have to rearrange this. First step, get t out of that dang denominator. How do you do that? If I multiply this side by t, yay, those cancel out and t is gone. But of course, anything I do to one side, I have to do the other. And I know what you're saying now. You're like, Miss Waters, how did that help us? T is not all by itself. So what was the point of that? The point of that is to get t over here so it's in the numerator, not in the denominator. And now we can get rid of that v and make the t all by itself. So what do we got to do? Right now we're multiplying t by v, so opposite is divide by v. Anything I do to one side, got to do the other. Yay, those cancel. Okay, and we're good. So what does t equal to? T is equal to distance divided by velocity. Okay, so that's what we get. That's our new equation. So let's plug the numbers into that equation. So time is equal to distance divided by velocity. The distance we found was 5,000 kilometers. And the velocity is 30 kilometers per hour. Okay, what does that get us? That gets us 166.6 continuing. What's the unit there? What are we left with? This was in kilometers, this was in kilometers per hour. So we actually are just left with hours. Okay? However, it says how many days does that take? So I want what is 166.6 continuing hours in days? Well, how many hours are in a day? There's 24, right? So I know for every 1 day, I have 24 hours. So that means I need to take this 166 and divide it by 24. 166.6 continuing, divide it by 24, and I'm going to get how many days that is. So let's do that. And we get 6.94 continuing days, but of course now we got to look at how many significant digits we need. This guy has 2 significant digits. This guy has 4. We were dividing, so we need the smallest number of significant digits, so we only need 2 significant digits. So finally, this is 6.9 days. So almost a full week to travel across. And there we go. So that's something that you are going to have to do, where you're going to have to take this 3-variable equation and rearrange it. So if we look back at this slide, we know that we have our v equals d over t, of course, that's the one here. But if we want to rearrange this, we just found out that t is equal to d over v. And if you guys didn't realize, we actually, while we were solving for t, actually came up with an equation for distance as well at some point there. At some point we had distance equaled velocity, or sorry, speed times time. So those are actually the 2 other equations you can get from this, and you could be expected to use any of them and rearrange for any of them. So just be aware of that. Otherwise, you guys, that is average speed, and that's where I'm going to stop today, and uniform motion. So good luck on working on the questions about this. And I'm going to talk to you some more tomorrow. You'll definitely be hearing my voice more, so hopefully you're not sick of it yet. But we'll see you later.